Good afternoon. I am thrilled to be here. It's so exciting to see the sea of faces, the students, the young faculty, because what I see in front of me is the future of computer science, the future of computing. So thank you for having me here. I am going to try to keep you awake. And actually what I want to talk about is what I believe are the ways in which we think about research in computing and related disciplines, what kind of impact we have on science, society, and technology. I like to talk about the drivers of computer science research. What drives us to ask a particular question that we work on in research? I like to talk about the science drivers, deep questions that we ask ourselves in computer science that keep driving us as a field. I like to talk about the technology drivers. As technology advances, we ask new questions because of new technology. We ask old questions and get new answers because of advances in technology. But most importantly, I like to talk about societal drivers. People, we have high expectations of our computing and information technology. And also, societal grand challenges can benefit from the advances that we make in computer science. But these drivers I talk about initiate the kind of research questions we ask: science questions, technology questions, and societal questions. So science, technology, and society are also ways for us to look at the impact of our research. So what I'm going to do in my talk is give you 4 short stories: a science impact story, a technology impact story, a society impact story, and one story that goes through the whole cycle. Before I do that, I wanted to remind you of the mission of Microsoft Research that Rick Rashid shared with all of you this morning: advancing the state of the art, technology transfer, and ensuring the future. I very much believe in this mission of Microsoft Research, and it so nicely maps onto the science, technology, and society drivers and measures of research impact. So I believe that Microsoft Research is a unique research enterprise that really subscribes to doing fundamental, basic, open research where researchers are driven by these kinds of questions and have impact on science, technology, and society. And all of us who do research in computing can have this kind of impact. So let's start with impact on science. And this story, all the stories, by the way, are results that I'm reporting from 2013, just this year. So these are very current research results that I'm reporting. This one is a breakthrough result in theoretical computer science that happens to have a profound implication on quantum mechanics. So that's why I call it computer science meets quantum mechanics. It's actually the question of splitting a quadratic form in half. Technically, that's what it's going on. And so let me just walk through very briefly and simply the idea behind the theorem they prove. So imagine you have a set of short vectors here that you see. It turns out that it's possible to partition this set of short vectors into red vectors and blue vectors such that in any test direction, half of the energy comes from the red vectors and half of the energy in that direction comes from the blue vectors. So that's intuitively what it means to split a quadratic form in half. Now, I talked about test directions and energy, so let me just walk through those concepts a little more slowly. Let's consider these 4 vectors in two-dimensional space. I can compute the energy along any test direction. For instance, along this test direction, pointing along the x-axis, I can compute the energy. It's about 1. And that's because the vector lying on the x-axis contributes its energy, if you will, but the 3 vectors orthogonal don't contribute as much. If I looked at the test direction along the y-axis, it's got more energy. So I hope you get that intuition. It turns out that what you can do is you can draw an ellipsoid around these vectors whose radius is equal to the energy in that direction. And a quadratic form is just such an ellipsoid. And now I can state the theorem. The theorem that a Microsoft researcher proved along with 2 colleagues from Yale University says that if you are given a set of sufficiently short vectors such that in each test direction the energy is equal to 1, then it's possible to partition this set of sufficiently short vectors into 2 parts, the red vectors and the blue vectors, such that each part has energy close to half in each direction. It sounds like a simple theorem, but it was actually quite hard. And if you look at the proof, it's quite sophisticated. Why am I telling you about quadratics and energy? It turns out that you can encode many, many structures in actually from many different disciplines as quadratic forms. For instance, in computer science, we work with graphs all the time, large social graphs, for instance. And a typical computer science question is to take a large graph and to break it into smaller graphs, subgraphs, such that each subgraph shares a property of the original graph. So for instance, in the graph sparsification problem, I take a big graph and I divide it into subgraphs. Each subgraph has the same number of nodes, but fewer edges. And it turns out that you can do this and preserve the cut property of the original graph. And this kind of decomposition that we do in computer science occurs over and over again. It's a way that we can then run algorithms, for instance, on the smaller graphs and run those algorithms much more efficiently than if we were to have to do it on the larger graph. This encoding of other structures as quadratic forms also shows up in signal processing in terms of the discrete Fourier coefficients, such that it underlines the classical uncertainty principle in signal processing that says a signal cannot be localized easily in both the time domain and the frequency domain. But probably most exciting to the world when this breakthrough theoretical computer science result was published just in June this year was that it proved an outstanding conjecture, the Katenzin-Singer conjecture, that has been outstanding for 54 years. And this theorem that was proved implies that the conjecture is indeed true. And why it took so long to prove this conjecture is that people didn't think it was true. And so this is a very surprising result, and this result actually speaks to the mathematical foundations of quantum mechanics and has other implications to mathematical physics and functional analysis. So that was my science story. Let me turn to something completely different, impact on technology. And this story comes out of Microsoft Research Asia, some work done that was published in this year's SIGGRAPH on video stabilization. The problem is this. Everyone has a cell phone, a tablet, some kind of portable mobile device with a camera on it. And we take pictures or videos, and what usually comes out is pretty shaky because our hands move around and we move around, and this is what you get. Now, wouldn't it be nice is if we could use in software, if we could use software to actually stabilize this video. And the technique I'm going to show you does exactly this. And so we can get rid of tripods and other physical devices because we can do the stabilization in software. So I'm just going to very quickly walk through the method that's used to affect this video stabilization. The typical pipeline in video stabilization is to take successive frames in a video and to compute a single camera path from frame to frame to frame. So you get a single camera path for the video. And then you smooth out the path. And then along each point in this smooth path, you actually warp the image appropriately to get a smoother video. So this is a typical pipeline that is used for video stabilization. And the technique I'm going to show you beats existing competitors along many properties that I'm going to show you by using two different techniques, two different ideas. The first idea is instead of computing a single camera path through successive frames in the video, we're going to compute multiple camera paths by taking each frame and dividing it into a 2D grid mesh, and then treating each grid in that mesh as a little video. And then from frame to frame to frame, we will compute multiple camera paths. So that's the first idea. The second idea is to use what's called adaptive filtering. In current techniques, low-pass filtering, like Gaussian filters, are used to smooth out the video. But if the camera moves rapidly, then you get these black areas and you get cropped videos and so on. It doesn't look so pretty. The technique out of Microsoft Research Asia uses what's called anisotropic filtering, adaptive filtering, and you can see that it's a much smoother path. And it doesn't have those black areas, and it doesn't have as much cropping. So with combining these two ideas together, we get better parallax handling. So what I'm going to show you now is the original video on top, and the best competing algorithm on the lower left, and our algorithm on the lower right. So you can see when a video has different, when you're looking at a picture and the perspective of what you're looking at depends on the direction you're looking at, because of the anisotropic filtering, we get better parallax handling. The second advantage of our approach is less geometry distortion. So when you look at the lower left competing technique, look at where the red arrows are, and you'll see that there's a lot of global skewing and global shearing and other local distortion. See that tree looks bent there. Also, there's less cropping with our technique. Again, if you think about these rapid camera motions, you can see how our technique does much better. And finally, in cell phones right now with CMOS technology, There's what's called a rolling shutter problem because images are stored line by line. And so we can actually correct for this rolling shutter problem. And you can see the difference between a competitive approach and our approach. Our approach is a lot less jerky. And here are just a few more examples of some input videos. And then, if we wait a little bit, we'll see our technique, the video stabilization technique, smoothing what you see. We can do people too. Good. So now let me talk about a story on research, also published this year, that has the potential for great impact on society. In fact, great impact on China. It's called UAIR in the grander scheme of a new emerging area, which I like to call, and others like to call, urban computing. This was work published in this year's conference at KDD. So the problem is not unfamiliar to many of you in China, and that is bad air quality. And so bad air quality is bad for society. I believe that. So the question is then, what can we do about that? Well, if you look at Beijing, Beijing has 22 air quality monitoring stations, and they're in fixed locations. And that's fine. If you're near one of those 22 air quality monitoring stations, you'd actually know how bad the air is. But most of us don't live near one of those 22 stations, and we don't work necessarily near one of those stations. So what we'd really like to know is where I am, where I'm living, where I'm working, where I'm eating at a restaurant, where I am walking through the park. I'd like to know what the air quality is where I am now. And so that's the problem that these researchers were trying to address. And what's so timely is this technique that I'm going to explain to you takes into consideration the multiple data sources that are around us. And these streams of data are then going to be used to create a model from which we can actually answer that question, what is the air quality where I am now? And there are different kinds of data sources. There are temporal sources and spatial sources. So in particular, in this technique, we're going to use meteorological data about the weather, air pressure, so on, traffic data, where the cars are right now. We're going to use where people are by monitoring the GPS on their cell phones. And then, of course, those are the temporal data sources. And then, of course, we might as well use spatial data, where parks are, where restaurants are, where the buildings are, the points of interest in a city. And of course, we also have the roads, the network of roads. They also don't move, but they're very important because they let us know where cars might go. We also will actually, of course, use historical data from the air quality monitoring stations and real-time data as the 22 stations are reporting their numbers in real time. And then what we're going to do is actually take Beijing and divide it into a big grid, and then compute through a model what the air quality is where I am right now. So the methodology is to partition a city into disjoint grids and to extract features for each grid from its impacting region, which is, just think of it as where I am plus the 8 neighboring regions around me. And the features are going to be, as I mentioned in the previous slide. And then what Yu Zheng does, and his colleagues do in this work, is to create a semi-supervised learning model that takes into consideration both temporal and spatial data. And this is going to allow us to predict the air quality index for any grid in that region. And they do it for nitrogen dioxide, sulfur dioxide, PM2.5, and PM10. And so just to show you that the features that they extract actually correlate intuitively with respect to each other, I'll just show you this one result here that plots 4 meteorological features: temperature, humidity, pressure, and wind speed. And basically the way to read this is to say, well, look, one result basically says when it's windy out, the air is good. So green dots are good and purple dots are bad. And that intuitively makes sense because when the wind comes, it blows all the bad air away. Similarly, you can read this plot to say that when the humidity is high, the air is bad. And that's also intuitive. So what they do is they create this semi-supervised learning model. And basically what that means is you have some labeled data. That labeled data comes from the 22 monitoring stations. You feed that labeled data into 2 separate classifiers. One is your temporal classifier, and one is your spatial classifier. And then you use inference to infer labels on the unlabeled data. You take that newly labeled data, feed it back into your training set, and iterate. And so then you can create this co-training semi-supervised learning model. They evaluated this model on 4 different data sets, 4 different cities in China: Beijing, Shanghai, Shenzhen, and Wuhan. And they got very good results in comparison to other kinds of learning models. So the black bars are the results from the model I just explained to you. And so if you're interested, you can actually go to this website and find out in real time in one of their neighborhoods in one of these 4 cities what the air quality is. So if you had your Surface Pros out or your laptop out, you could actually do this right now. Okay, let me now talk about one last story on the impact of science, technology, and society. And I like this story because it relates to a question that Rick Rashid was asked this morning about does everything people do in Microsoft Research have something to do with the company? And in a basic research organization, the answer is no. Remember, the first mission statement of the Microsoft Research is advance the state of the art in whatever area you choose to do research. So I'm going to start with a story about how fundamental research in visualizing data for astronomers ended up in Excel, technology that Microsoft produces and sells, and how this circle can be closed by this visualization technology having a potential for policymakers to make decisions about their local region, about their city, for instance. So we start with the astronomers. Many years ago, astronomers for centuries have been collecting data. And of course, most recently, astronomers have been using very sophisticated scientific instruments like the Hubble Space Telescope you see on the left and the Sloan Digital Sky Survey you see on the right, collecting lots and lots of images of the universe. And there are multiple such telescopes on the ground and in the sky and so on. And years ago, Microsoft Research, along with researchers at Johns Hopkins University, asked the question, why don't we try to visualize the data that all of these instruments are collecting. And that led to what's called the Worldwide Telescope. It's a way in which you and I can visualize the universe. In fact, it's a way that you and I can take a virtual tour through the universe. And I'm going to show you an example soon. Before I get to the tour, I do want to say that the Worldwide Telescope is in use in China. There is the first Worldwide Telescope dome is in the Chongqing Planetarium. And there was an event last week that showcased the Worldwide Telescope there. So now let's look at a kind of tour that one can take through the universe using the data visualized through the Worldwide Telescope. Oops. Uh-oh, how do I go back? Thank you. Okay, I think it's playing. So we're taking a trip through the solar system, to our solar system through many galaxies. There are millions of galaxies we just went through. And each galaxy contains billions of stars. And what we're going to zoom in on pretty soon is we're going to come to our own galaxy, the Milky Way, and we will see our solar system in one of the spiral arms of the Milky Way as we approach, there we go. And then if we continue zooming in, we'll pass by our planets that are near the Earth. For instance, here's Saturn coming up. And you can imagine all the different telescopes collecting all these different images, and then we, through the Worldwide Telescope, have been able to stitch together everything so that we can enjoy this tour to Earth together. Well, this was pure research. It was about astronomy. It wasn't even about computer science. And in fact, the Worldwide Telescope is used by citizen scientists around the world. Many, many users. And the aha was, why not, point this telescope that's looking at the sky to the Earth? And why not do a similar kind of data visualization from all the data that we have about the Earth, about countries, about cities, and so on. And that was what brought us to taking this pure research, pure scientific research work into Microsoft technology. In particular, in Excel 2013, there's a button you can press called Power Map, and it basically allows you to visualize any data that's represented in an Excel spreadsheet. And so let's look at some data from China's 2008 Beijing Olympics. We're going to look at where in China the medals were won. Whoops. Okay, so hopefully this will play. Here we go. Okay, we're going to zoom in, and we'll see, first of all, China won 74 gold medals. But now let's look at which provinces won medals, gold, silver, and bronze medals. And we can see that almost every province can brag about having won medals. We'll see that, I have to read this, Liaoning won the most medals. But if we look at a breakdown of the gold, silver, bronze medals, we'll actually see that Jiangsu won a proportionately larger number of gold medals. We can even look at a breakdown of the kind of sport where these medals were won. So you'll see Shanghai has a lot of water sports medals, and Hubei has a lot of gymnastics metals. So this is the kind of visualization you can do once you have data. The next example I want to show has more to do with, so what? You look at this data, isn't that pretty? But in the end, you want to make a decision about the data you're visualizing, about the information that you're seeing that's much easier. You can make these kinds of policy decisions because you can more easily see the data. And so this is an example from Seattle, which it's about traffic accidents in Seattle. And you'll see as we zoom in here, let's see if this works. Oops. Oops. Back. Play. Back. No, back. It should, when you look at the black screen, it should be just play. Okay, it's the black screen, just play. Okay, we go. Oops. We'll get this yet. Okay, play. No. It's not really that exciting. Okay, here we go. And you'll see over this 2-year period, the traffic accidents. We're going to zoom in on 4 places where there are high numbers of traffic accidents. One here in this play field, one in a very busy intersection in downtown Seattle, and one coming up near a community college, and one coming up also near a mall. And it turns out that when we showed this data to the local neighborhoods, in fact, at the community college and the mall, they put in traffic lights. Once they had this data, they made a policy decision. So this is fairly new. It's only in Excel 2013, but already oil and gas companies and finance companies are using Power Map to make these kinds of corporate level decisions. So this is my science, technology, society story. But now let me move on, looking to the future, and I was very gratified to hear the questions from this morning from the students and the faculty who wanted to know about where's computing going for the future. And what I'm going to do is just share with you some trends that I see. Let me start with the science questions. These are not trends. These are outstanding questions that kind of underlie our field. I wrote a little paper. It's only 3 pages long to address each of these science questions. So I'm not going to go through each of these one by one. But probably the most fundamental question in computer science is what is computable? What problems can we solve with a computer? And what problems can we not solve? And what's interesting about that question is you'd think that we know this answer. But if you listen to Professor Joseph Safakis' talk this morning, our whole notion of what a computer is, a model of computation, is changing. So if we might know the answer to this question with respect to a Turing machine, but suppose we open up our thinking and think about humans and machines working together as a computer, and then all of a sudden answering the question, what is computable, is very difficult. Let me look at some technology drivers or trends. So let's just look at machines and devices. At one end, we've got exascale computing coming. And in between, we've got multiple kinds of devices that people wear, people carry. And then at the very extreme end, we've got nanocomputing coming. We've got biocomputing coming, where people are using molecules to program functions, computable functions. And now imagine putting bio, nano, and info together. And I think the real tease out there is, of course, quantum computing. So the future is, there's a huge future ahead of us because we can hardly scratch the surface on all of these. In terms of technology trends of scale and intelligence, Well, we talk a lot about big data. We're drowning in data. And I think what's more interesting to be asking is not how do we extract knowledge from data, but how do we make decisions or take action based on the knowledge that we extract from the data. And the Worldwide Telescope Power Map example gives us a hint of what's to come. Of course, there's the cell plus the cloud. And again, Professor Joseph Safakis talked about cyber-physical systems this morning, or smart X. This is another trend to expect when we've got computing interacting with the physical world. Robots are coming. And I very much liked Roz's talk about thinking about what's going on in the brain. I think computational neuroscience is a new emerging area with lots of research questions to answer. And finally, I've already hinted at this notion of a computer where you've got humans and machines working together. In fact, networks of humans and machines working together to solve problems that neither can solve alone. And finally, let's look at societal drivers and the kind of impact we in computer science would like to have on society. We have trends like all of us having high expectations of computing and information technology. We expect everything to be 24/7, usable by anyone. We want access to anything at any time from anywhere. And in reality, we don't quite have that. Our systems are still unreliable, our connectivity can be down, servers can go down, we still get blue screens, and so on. So we have a long way to go there as well. Another societal trend is, of course, our computing technology is really useful and used by everyone in society, from the old and the young, the rich and the poor, the literate and illiterate, the able and disabled. And another trend is, of course, highly personalized computing, personalization. And I think this is going to happen with the use of big data, techniques like machine learning, and so on. Let me close now with what I think are truly our grand challenges, and my hope and wish that the young people in this audience who still have long research careers ahead of them will think about addressing, because I do believe that these societal grand challenges like energy, the environment, climate change, food, water, healthcare, education like MOOCs, transportation, and safety and security, these societal grand challenges will be helped by advances in computing and computing technology. Thank you.